Cool. Can everybody see my screen?
Yes, looks good.
Yes.
Maybe a little little small in the font size though.
Oh, absolutely, yeah. Cool. Awesome. Welcome, friends. This is Deep Learning Adventures and Fun Engaging Meetup, where we talk about data science, machine learning, and deep learning. For the last couple of months or three months, if I remember correctly, we've been taking these Kaggle Mini Courses, which is a series of very short self-contained units covering anything from basic Python skills to data visualization to data standardization and cleaning. We've covered geospatial analysis, and we delved into machine learning, some introduction to NLP and deep learning. And last session, which was a couple of days ago, we covered computer vision. So today we'll cover two Kaggle competitions related to computer vision and a special hardware architecture that is used for these competitions called TPU, or Tensor Processing Unit. If you're joining us for the first time, welcome. I want to make sure if you're welcome. If you're joining us from YouTube, welcome again. I also posted this on Kaggle, so if you're joining us from Kaggle, welcome, and hopefully this is useful to you and your Kaggle adventures. All our sessions, including this one, are recorded, and I'll post a link pretty soon on the chat here. They're available on our YouTube channel here. You can see we have 16 videos so far, a couple more to wrap up this Kaggle adventure, and then we'll move on to an NLP adventure, as you'll hear towards the end. We just want to thank everybody for coming, especially my great co-organizers, David and Robert, and thank you everyone, especially if you're joining us from a different time zone. Appreciate the effort and the sacrifice you're making to be with us here. Let me post a few links for us to look at. So I posted both the channel, the YouTube channel, as well as the Slack invitation if you want to join us on Slack. We're pretty active there. If you have any issues with code, or if you want to share anything about new events, or if you want to share anything new you learned, feel free to share it with us. We always enjoy learning from each other. Let me zoom in a little bit more. So last time, if you remember, we covered computer vision. David and I went over this few sessions. We covered convolutional neural networks, pooling, sliding windows, custom covenants. We built our own custom convolutional neural network. We talked a little bit about data augmentation. And we saw that with each step, we saw our validation accuracy increase a little bit as we progressed. So today we're going to talk about these two bonus lessons, or two bonus sections. One is about a competition called Petals to the Metal, and the other one that Neil will lead is on this Cassava leaf this season. If you remember, we tackled this a while ago, so it's good to see it again as a new competition. So this first competition is about getting used to image classification and also getting used to this new hardware infrastructure called TPU, Tensor Processing Unit. There's a sample notebook here that a lot of people, especially including myself, rely heavily on by Ryan. He did an amazing job of covering the basics of reading the data, displaying some data, looking at the training and validation data set, working with TPUs, and training a basic model from a pre-trained model. Instead of going through this notebook, I will go over my notebook, which again builds on this, but it has way more features added to it. But before I do that, let me just guide you a little bit on this competition. What is it and what does it look like? So I think this started, it's an ongoing competition, but I think that the leaderboard gets reset every month. I didn't know that. So David, thanks for letting me know. There's a few links here. If you are new to TPUs, or if you're new to Kaggle, and the goal is, the goal is to predict about 100. There's 104 types of flowers, and the goal is to basically build a computer vision classification model to classify correctly each of the flowers, and we'll see some samples pretty soon. The evaluation is done on F1, which is a combination of precision and recall, and the submission file is just an ID of the image, as well as the the label, the class 1 out of 104, just an integer. You're highly encouraged to use TPUs because you're going to use, we'll use, as you'll see, data that is stored in a TF record format, as well as it's image-based, so TPUs are pretty good at handling both. This is just some differences between the two leaderboards. There's a private leaderboard and a public leaderboard. The data, unfortunately, you cannot browse through it as it is here, but there's a training folder, there's a validation folder, there's a test folder, and the sample submission file that you can see here, where you have the ID of the image and the class of the image. There's a few notebooks. Cool, I'm trending. Thanks for your help. I love your votes. If you could, finally got my first silver medal. I'm aiming for the gold one as well. All I need is 20 plus more votes. It's just based on votes.
Are those medals for specific to a notebook or overall achievements?
For notebook, yeah, for this specific notebook that we'll cover today. And I also shared this session that we're recording today. I shared it on Kaggle so that people later can find it and comment on it. Cool. Leaderboard is pretty active. People are, the top one is 0.98 score, macro score. And let's see, I am 34th here, 0.95. So took me a while to get here. I used a lot of different methodologies I'll cover today. And I have a few more left, so should be fun. Cool. All right, let me zoom in. This is the notebook that I shared on our chat, as well as that you saw in the Kaggle competition. So I'll give you the overview of how I tackled this. So first of all, I was already a little bit familiar with TPUs. If you remember, we did particle detection, Higgs boson detection using TPUs. So we exposed ourselves a little bit to that. But as well as Ryan's notebook here was very useful in understanding how TPUs work, and we'll go through that. And the other thing is I covered over 10 models, transfer learning over different 10 models that TensorFlow offers, 2.2. I also tried learning, instead of freezing the layers, I also tried end-to-end training from scratch for this large architectures. It took a while, but as you'll see, it was worth the time. Then I shifted gears to hyperparameter tuning, as you'll see, data augmentation, different learning rate schedules, and some other cool techniques. I combined all of them, and I created this nice visualization for us to look at. I reached out to a lot of Kagglers, so I want to thank them. You'll see them, I specifically mentioned them in this notebook. But I learned a little bit from each other notebook that I came across, and I want to make sure that I thank them. I also promoted our community, built some cool 3D visualizations that we'll get to explore. And I have a few more to-do lists that I hope to get at some point. So again, if you find this useful, please upvote it. Cool. If this is new to you, or if you just want the summary, I have a chart here where, let me zoom out a little bit. On the x-axis, I have the different models, and you see I have Resident 50, VGG 19. The basic notebook, I think, was using VGG 16. Some neural architecture search, Inception, Exception, MobileNet, DenseNet. And then ResNet 201. And then, as you'll see, it's basically two models with different tunings. The numbers that you see here are the tunings that I use, and I have a legend here, and I'll go through that step by step with you. So as you can see here, I'm just plotting the validation accuracy, and as you can see, with different tunings that I did with different models that I explored, I was slightly getting above 80, 0.8, 0.85, 0.9, 0.95, and EfficientNet B7 was the one that got me the best so far with validation accuracy in 0.96. But the one that got me the best on the leaderboard was the ensemble of EfficientNet and DenseNet 201. Cool. Let's dive through this real quick. Talk a little bit about the different tunings and different models, as well as.
Rich, quick question before you go on.
Yep.
So do you, I don't know if you were calculating the leaderboards based on the F1 macro score.
Mhm.
And this is validation accuracy. Is this just regular categorical accuracy?
Yeah, I think so. Yeah.
Okay, that's great. The only reason I was asking it's interesting sometimes to know if the validation set and the training set have the same kind of distribution as the test set. So for instance, if you do well on a validation set, are you gonna see similar type of performance on the test set where you're scored? Are you seeing, have you confirmed that, or just, I'm just curious?
Yes. So from my experience, both the training, validation, the test set have very similar distribution.
Excellent. That's what you want. Yeah,
Yeah,
great.
that's what's made this competition challenging and interesting, to be honest.
Okay.
And I assume that you tried all of these models sequentially in the order that we see them going across the page here.
Not in this order. I have this is sorted by performance, so not necessarily in this order, but in one of these different orders. Yes, sequentially. I couldn't do them in parallel. And the size of the circle is the F1 score as well. So I'm tracking precision recall and F1 as well.
Looks like you definitely used a lot of TPU hours there.
I was I exhausted my 30 hours a week for that week, which was the week of the last week of 2020.
Oh, nice.
Yeah, cool. I have some 3D visualizations. They're not interactive. I'll go to them in pretty soon, the interactive mode, so we can zoom in and zoom out. But I just want to show you how the end result looks like. So we have an image, a flower, and over it, you're going to see the title and okay if we predicted okay, or in this case, this wild rose not if we did not predict it okay, and what is the right class, in this case, it's iris. So this is how the data looks like. You have an image of a flower. It could be from far away. It could be from close up. It could be, look at this, from a field. Could be maybe with somebody in the background. They vary. Another thing that I wanted to show you is out of these 104 classes, what is the distribution of the classes? Actually, this is the inverse of the distribution. So you see, it's not really uniform. We don't have a good representation from all different classes. It's I would say a little bit imbalanced, especially for this 40 to 50 range or 60 to 80. So that will make it a little bit more challenging for me. Cool. Another thing that we'll be plotting is this confusion matrix where we have 104 labels on the x-axis and 104 labels on the y-axis. And for what is the number of, so for each combination, what is our prediction? What is the correct label? And hopefully we have this nice diagonal image which says that out of all the correct labels, we identified most of them as the right label. So basically that means that if something was a tiger lily, we identified as a tiger lily and not as an orchid or something else. And also F1 precision recall, we're going to print it out. Cool, just flagging for our community here. And then let's dive in. So some libraries we're going to use, some visualization libraries, as well as pandas and NumPy, just for tracking our performance. TF, if you notice TF, Kaggle recently updated their TF version. If you go to the TensorFlow website, the latest one I think is 2.4. And Kaggle was running on 2.2 for a while. Oh, I guess it's still running on 2.2. I think at some point I saw it 2.3 there. I don't know why it's 2.2 today.
So if you're using a regular CPU, it's going to be 2.3.1, I think. But they started to move to I think it's 2.4 on the regular CPU. But when they moved to TPUs, they were seeing, when they went to 2.3, 2.4, they were seeing memory issues in 2.3.
Oh, really?
So I think they're still testing. 2.4 is supposed to fix it for them. And so they're testing that. So it's stuck on 2.2 currently when you use the GPU environment.
That'll explain, because I remember a few days ago it was 2.3, but now it's 2.2 back. Okay.
Yeah.
Cool. In terms of a little bit of the hardware, we're going to use this TPUs, and you can enable them in your Kaggle notebook here. You can do none, which is a CPU-based acceleration, a GPU-based acceleration, or TPU, what is called version 3.8. And that means that this TPU has actually 8 cores that act as accelerators. Some more information here about TPUs. I'm not going to dwell too much about on this, but basically what we need is we need to connect to our what is called our TPU cluster locally, which is running behind the notebook. We need to get some information about it, some IP, and as well as how many replicas are running, how many cores are running in this TPU. If we're not running TPU, this would be 1, but we're running with a TPU, so we have 8 cores available. The other thing is, I think this is a Kaggle library. We will use this TPU getting started data set, which is basically hosted on Google Cloud or Google Storage. And you can see here the URL for it. I'm going to use it. I'm going to look at some examples. These are some tunings that later I'm going to try. I'll go over them later on. But our data is basically stored in this TF records. And let me see if I can. Yeah, so you see here we have a TF records for different image sizes. We have a 512 by 512, 331 by 331, 224 by 224, 192 by 192. And then within each subfolder, we have a train test and validation. And within that, we have this TF record files, which is a collection of multiple images. So TPUs are equipped with 128 gigs of high-speed memory. They allow us to work with relatively high resolution images like 512 by 512. Usually in computer vision applications, you see much lower resolutions, but with the TPU, we're able to do this. We're also, by setting this parameter num parallel reads auto, it helps us read multiple files as data becomes available from Google storage, Google Cloud Storage. If we're not interested in ordering the data, maybe, for example, during training, we're not really interested in the order since we shuffle data anyway, we can set up this experimental deterministic false, which disables the order and basically allows us to have higher throughput and pulling data in our TPU from our Google storage.
George, quick question for you. So up in the right, there is a monitor that shows your usage of CPUs, TPUs, memory, and the hard drive. Have you successfully been able to turn that TPU very large red or green?
Yeah, I think I was able to turn it 60, 70, maybe 80%.
Oh, that's
I was not able to do it 100%.
No, that's really good usage. 80%. That's really
yeah, I think so. Yeah, but that's only during training.
Sure.
Yeah, good point.
That's when it counts.
Yeah. So image size 512 by 512. We're going to have that Google Cloud Storage path. The folder we're going to use is this TF records. We've seen this auto-tune experimental feature where we are basically able to fetch data in a more efficient way from our storage location. And then the 3 different locations, we have a training location, a validation location, and a test location. And the different classes, there are 104 classes here. This is just a list of strings of different classes. So we have Carnation, Petunia. Many of them I still had no idea existed. So it's good for me to expose myself. And this reminds me of a movie I was watching over the holidays. It's called, I think, The Big Year, where people are detecting birds. It's with Jack Black, I think. Yep. This reminds me of the flower version of it, where you look at these exotic flowers all around the world. Then some code to read the data and decode it. I'm going to read it as a JPEG. I'm going to divide it by 255 so that we can convert our images to 0 to 1. If you remember, our deep learning models work best if we have a contained range of values, and just reshape it to a 512 by 512 by 3 for RGB. These are color images. If you remember, the TF records have a structure within them. In this case, we have an image and a class substructure. And the image is just a byte string, TF string, and the class is just an integer, 64, 0 to 103. The unlabeled ones just have an image and ID. We don't have a class for them. And then the way that we're going to load this data is going to read the data set. There are some options we can set here for efficient reading and apply one of the methods if it's labeled, otherwise unlabeled, and return that data set. Going to look at some examples here. The other thing is we can do some data augmentation if we want. I can come back to this later. I think it makes sense if I come back to this later. So ignore for now. There's a data augmentation version 1, data augmentation version 2, data augmentation version 3 for now. For most of our models, I went with a very basic flip left-right image, which basically takes the image and flips it horizontally. You can get fancier. There's 3 more versions or 2 more versions that we're going to explore. But even with just a basic data augmentation method like this one, I got pretty decent results. Then how we're going to load the training data, we'll bring in the data from our training location, Google Cloud Storage. I'm going to shuffle them. Batch size, I think, is
16 times the number of.
16 times the number of.
Times 8.
Times 8.
Usually 8, yeah, depending on the chip you have, but in this case we have 8 replicas.
So 128. This should be 128 then.
So a lot of the parameters we're using here are just to get the most efficiency out of the TPU, the batch size, and putting things into these TF records. There's a lot of kind of kid handling of the data to make it work well on the TPU that you don't have to deal with on other devices.
Yeah.
The other thing of note there is, I don't know if people notice, but the data needs to sit over on the Google Cloud for it to actually work well with the TPUs, right? It has to be hosted there. So it's not just local.
The original format was just JPEG files, and you converted to TF record.
No, there were TF records.
TF records in the first place.
JPEG. Internally, they're JPEG, but I think they're collectively.
They give it to you already in TF records.
In TF records, okay.
Yeah. And we have about 12,000 training images, 3,000 validation, and 7,000 unlabeled. So decent data set, not the biggest, but again, decent. Yep, that's the batch size, 16 by how many cores we have, and short explanation here of we want to make sure we utilize all our cores. So that's why we set the batch size to 128. Cool. Going to read the data into this object here, DSTrain, dataset valid, dataset test. And this is now a pre-fetched dataset. So it's an iterator. We have to iterate through it to actually get the data out of it. If I looked at one simple example or one batch size, how does it look like? It's a 128 images by 512 by 512 by 3. That's the image. And the label is just a batch size of 128 by a number. If we want to look at some sample data labels, it's just a list of integers. Same for the test, but the test now doesn't have actual labels, but it has image IDs. That's the only difference. We don't have labels for the test. That's our goal, to label them. Just some methods here. I don't want to spend too much time here, but basically based on if the label we predict is matches the one that is correct, we're going to display OK, otherwise a no, and display the correct label as well. And just some plotting settings here so that when we plot a 16 by 16, sorry, a 4 by 4 grid of images, it actually looks good. Some other methods here for when we train, we want to plot the history, we want to plot the validation and training accuracy. I added another one. We're actually plotting the learning rate schedule as well, because we'll be tuning that as well. Cool. Let's look at 20 sample images from the training set. So here we go. Common dandelion, passion flower, daisy, thistle. I'm not sure if I'm saying that correctly. Buttercup, camellia, iris, rose. There's so many kinds of roses. Mongolia.
Excuse me. TPU is turned on, right? Don't you want to turn it off during the explanation?
Sorry, I didn't hear you. Say it again.
The TPU is turned on, right?
Yes, yes.
Don't you want to turn it off during the explanation?
Well, I'm not running it. I ran it a couple of minutes ago, so.
So it's not, it doesn't burn, then you don't run it?
Yeah, it's not. Yeah, it's 0%.
All right.
Yeah.
Okay.
Yeah, don't worry. I'm not underusing it. Cool. Then just some sample data augmentation. One is the first version, data augment here, just looking at the same image, but randomly augmented. So this is, I'm doing a vertical flip, left or horizontal flip. So you can see sometimes the image is pointing left, sometimes pointing right. Version 2 does what is called this random blockout. And we'll go through that, but there's a paper here that I found on Kaggle where by randomly raising data, you actually get a slightly better performance in your image classification. Still not convinced how this works. So for us humans, it makes sense, but as you'll see in this data set, in few cases, the actual flower is hiding, like especially here, right? You can't really tell what you're looking at.
Might make sense to hide the bee because one of the images had bee on it, so probably it would address it in some way.
Yeah, so if I understood correctly, I haven't read the paper fully yet, but if I understood correctly, is you're not allowing your model to tune to specific features that maybe are not relevant. So by adding a little bit of noise here, in this case, no information, maybe it's picking up the background or the contrast and so forth.
Mm.
Another data augmentation is playing with the location, with the size, with the contrast, and you can see here in a few cases, you're able to detect the flower. In other ones, the contrast is just too dark or the brightness is too dark, and it's very hard for us, but maybe the pixel level you can still detect. Cool. I tried different models. The one that the basic notebook covers is this VGG16, which is trained on ImageNet. Ryan recommends some other ones, and we'll see the ones that I covered. For this application, I used this TF-Keras applications module. This is running 2.2, so it doesn't have all the cool models that you see in 2.4. 2.4 has way more. But I went through this list one by one, and I ran all this: DenseNet, Inception, MobileNet, NASNet, ResNet, ResNet 50, VG16, Exception. And if you click on them, let's say DenseNet probably has multiple versions underneath. Yep. So as a 121, 169, 201. I try to run the biggest architecture sometimes, just to make sure that I'm using all the resources. So again, this is 2.2. If you look at 2.4, if I can do this. I guess that's the latest one. Okay, 2.4. TF, where are you, Keras? There you are. Applications, overview. So you have EfficientNet, which is new in 2.4. I think you have some newer versions of MobileNet. I don't know if the other ones have. Yeah, but EfficientNet you have way more that you didn't have before in 2.2. Cool, yeah. So this is me exploring the different, the directory structure of TF-Keras applications, and you can see here there's different models, DenseNet, Inception, and so forth. I kept track of all these models by using this model checkpoint, make sure that I only save the best weight by monitoring validation loss. I also used early stopping when I was training a model, tracking validation loss, and if the validation loss didn't improve for 3 epochs, we stopped training. I was trying to track the learning rate. I found some information online about using for extending methods from TensorBoard, it didn't work for me. So I was able to extract the learning rate in a slightly different way. I also experimented a little bit with having my own custom callback for tracking the learning rate and so forth. As I mentioned, EfficientNet is not included in Keras 2.2. So if you want to use it, you have to install it from a GitHub repository. And that's what I did here. Another tuning 11 or one tuning is looking at the weight per class, which basically tries to penalize more your model if it's incorrect in a minority class, if I understood it correctly. So your model, when it does incorrect prediction on a majority or minority class, you shouldn't assign the same loss. You should give a higher loss to the ones that I think is underrepresented. So in this case here, we're looking at the raw data. I'm going to get a count for it. Then we're going to divide. So in the original approach that I found online for this weight, they use the number 122. I'm still not convinced why they use 122. Maybe from another data set or another competition, but I would use 104 here, divided by how many examples you have of that class. Let's say one flower could have 10. This would be 122 divided by 10. So it's the inverse of popularity, basically.
So I must have missed in the initial presentation. There's a lot of classes here, right? But is there also a large imbalance?
Oh yeah. Let me show you the graph. Yeah, this is the inverse of popularity, which is the weight. This is the weight basically. So, which is the inverse of popularity. So this one, for example, has a high weight. That means that's not as popular in our original data set.
So the most frequent examples in this data set might be the ones that have a weight of 0.2.
Yeah. Yep. You have the lower ones. Yep. Yeah, as you can see, it's not that balanced.
Did you plot out these? How much difference this made with using class weight versus not using class weight?
Yep.
Okay.
Cool. So that was the weight. Then the general structure was built a very simple transfer learning model using TF Keras applications, and you can see here the list, the long list. Let's say we want to use DenseNet 201, which for me performed relatively well. It's one of the top ones. We don't want to include the top layer, which does a classification based on ImageNet. The weights we want to preload are based on ImageNet. There's another data set that I'm going to use for EfficientNet. It's called Noisy Student. We're going to look at that soon. And there's a paper on Noisy Student as well. If you want to average the output of the pre-trained model, you can do it here. Or as you've seen in our previous example, in our last session, you can also do it here in the end. Our input shape will be image size, which is 512 by 512 by 3. This pre-trained model trainable, you can set it to false or true. If you set it to false, you will not retrain the model that we preloaded. If you set it to true, it will actually train it from scratch. And I tried both options. Then the actual model is just a combination of the pre-trained model and average pooling to lower the dimensionality of our data. Experimented with dropout as well. That's tuning 3. And then in the end,
George, just to clarify, you're not training from scratch, right? Because you have weights already. If you put weights equals none, then and did trainable equals true, then you would be training from scratch, right?
So I tried both with weights equals ImageNet. So I think it preloads the ImageNet weights, but then it allows you to modify them.
That's right. But you're not training from scratch. You're starting with.
Got it. Okay, yeah. Then I shouldn't say scratch.
If you want to train from scratch, you can put weights equals none, and that would allow you to train from scratch.
Got it. Yep. Absolutely right. I should correct my methodology. So I'm continuing to train with preloaded ImageNet weights. Awesome. In terms of optimizers, I tried both Atom and Nesterov Atom. That's tuning number 2. This is, I use sparse categorical coarse entropy because our classes are integers. And this is a classification challenge. And for metrics, I'm just looking at the accuracy. When I was training, I tried to get an idea with just a few epochs. Initially, I was running with 12 epochs just to get an idea of which model was doing better. And then once I figured out that there are 2 or 3 models that are performing well, I increased it to 30 epochs. Another thing that the default notebook had is this learning rate scheduler, which basically, I think there is a chart here, no? Which basically increases the learning rate linearly in the beginning. Let's see here. So if we are less than ramp up epochs, which is usually 5, then we do a linear increase of the learning rate. If we are in this, what is called the sustained phase, we stay flat. And then after that, we exponentially decay our learning rate. I think the original notebook has it. Let me show you, because that's an interesting graph. Yeah, so you see here, it starts linearly until the 5th epoch. Here, he didn't have a sustained period, or sustained period was 0. And then exponentially lowering it.
Sorry, and you're doing it while training, not just to find the learning rate for training, right?
Yes, so you'll see how I'm using it. It took me a while to understand this, but usually I was under the impression that Adam would take care of this for me, but Adam, the learning rate in Adam, you can actually tune the upper limit of it. So by default, Adam will figure it out, but what you're doing here, you're saying your upper limit that you're allowed to go is based on this learning schedule. And you're, as you'll see later on, you're bringing that upper limit lower and lower and lower.
I see. Thank you.
Then how we're training this, we have our training data and model fit, validation data, epochs, some callbacks here for checkpoint and saving the best model, as well as some learning rate callback, which sets, sorry, when I did, which sets the learning rate, yeah, in combination with Adam. And then wait for class, that's in tuning. I tried with and without it, and we'll see how that performed. In many cases, the performance was decent. I didn't see a lot of overfitting. I don't have them here because my last run was based on an ensemble model. And some other things that I tried was this weights for EfficientNet. I tried this noisy student version. Another thing that I tried was continuing to learn after loading ImageNet, continuing to train the model end to end. And I did that for both the EfficientNet on noisy student as well as DenseNet. So it takes about an hour to do this. If you don't do end-to-end training, it takes about, I don't know, 10, 20 minutes to train the model. But if you do end-to-end, it takes about an hour. So I did that. I stored the weights, and actually I'm importing them as input here. I have a repository on GitHub, on Kaggle, where I store these weights for both the EfficientNet and the DenseNet model. And as you can see here, the EfficientNet has 64 million parameters. I continue to learn them for 30 epochs. And the DenseNet had, I think, 18 million parameters, which again were trained end-to-end as well. Then I wanted to combine both of them. So looking at the validation data, using the first model predict, the second model predict, I wanted to explore a linear combination of the predictions for both models. And the goal was to find an alpha or a combination that gives me the highest score, the highest probability of a class. And as you can see here, this is just a plot of alpha and validation accuracy. So we are exploring basically 0 means use only one model. Use model M1, which is the EfficientNet. 1 means use model 2, which is the dense 201. And we range all the possible combinations within, one unit at a time, 0 to 100. As you can see here, for a combination of 0.35, I think, yep, I was able to get the best validation accuracy based on F1 score. That's how we score them. So again, we do a linear combination of our predictions. We pick the best one. Then based on the F1 score, we append it. And then for each combination of this alpha, we pick the one that has the best score.
So George, just to clarify, so you actually trained the models individually, trying to maximize just the straight accuracy. And then this step here, you're actually trying to combine the model, using an ensemble to combine the models. And here you're trying to optimize not accuracy, but F1 score.
Yep. Yep.
Is that right?
Yep.
Okay.
You got it. Yep. So the best alpha.
And you didn't try to tune the F1 score at any point when you were training them.
Well, when I was tracking
individually.
When I was training validation accuracy, when I was tracking validation accuracy, I'm also tracking F1 score. And usually when validation accuracy goes higher, F1 also goes higher.
Okay.
Yeah. Then just here on the test data set, how do you get the actual prediction of the test data set? You combine again both, use the alpha that we found from above. We pick the best of them, and then we generate our predictions. And the prediction it's a label of the image and the class of the image. Let's look at this confusion matrix. I think this might help clarify a few things. As well as F1 precision and recall. So for this ensemble model, I was able to get 0.96 F1 score, which is a combination of precision and recall. And as you can see here, the closer I am to this diagonal structure, the better. There are some cases where, for example, this one, it's actually yellow iris, but I think I classified it as a sweet pea, or maybe for another one. So you shouldn't see any or significant presence outside this diagonal structure. That's the goal. Cool. Let me talk about the different tunings and what do they mean and how do they score. I have a lot of notes here. So as you see here, every time I run a model, I'm tracking the model family, in this case, VGG, VGG16, how many epochs I ran it for, where did the loss happen to be the minimum, where did the validation accuracy happen to be the maximum. I wanted to see if I'm basically optimizing my model in the very beginning or early on. Basically, I need to figure out if I increase the epochs, could I still get a better accuracy? So for example, this one's here, if the closer I am to the epochs, that means that I could still go for it. What is the actual minimum loss and validation data set? Maximum accuracy, F1, precision, recall. So we have VGG, DenseNet, Inception version 2, Inception version 3, MobileNet version 2, ResNet. And then these are the 30 epochs one after here. And then the different tunings. And I'll go over that legend, what this means. 1, 2, 3 means I did some kind of augmentation with 1, 2, 3. 1, I think, is using learning rate schedule. 2, using an atom instead of atom. 3, I don't remember 3, so I have to look at the legend. Overfitting is OF. I think this was the only one that I clearly saw a sign of overfitting. And the other ones I did not see. So actually, let me look at, yep, so that's the performance table, but I'll go to the visualization, which has an explanation of all these different tunings. But as you can see here, I started with just 12 epochs and 30 epochs, and then tracking both accuracy and F1. I also added some annotations here. So now we can dive into this tuning legend. So tuning one was, this didn't make a difference for me if I specified pooling equal average in the base model or doing the global average 2D, that had zero difference for me. The other one that I used was exponential learning rate or not. And that, I think, made a difference for tuning one. Tuning two is if you use atom or natom. So two means using the instead of atom. Tuning three is if you're actually using a dropout after the global average pooling and before the last classification layer. Tuning four is if you use version 2, which is the random blockout. Tuning five is there's a feature in Keras where when you read or when you train the model, there's an option to set up the workers. It didn't make a lot of difference for me. I think this would make a big difference if we actually running this in production with a much larger cluster. I think since we're running this on a single instance, this did not speed up things for me. And I have the links in the notebook of more about this. Tuning 6, which I haven't tried yet, is using additional data. Hopefully that will give me better performance. Augment version 3 is the contrast that we saw and the shearing that we saw. Tuning 8 was end-to-end training where I preload the weights of ImageNet or Noisy Student, but I continue to train all of them, even in the convolutional backbone. Tuning 9 is using this more newer model, EfficientNet. Tuning 10 is using Noisy Student instead of ImageNet, and 11 is using that weight per class. So having understood that tuning legend, now let's see if we can understand what am I looking at here. So the first few models, and I'm not sure why they underperformed so badly. Could be a weight initialization, I'm not sure. There's no tuning at all, just a basic model. And we are just training the head, we're not training the backbone. So we tried VGG 16, Resin 50, 19, is NAS netball. And then we're still in the 12 epochs, Inception V2, Inception V3. Let me zoom out a bit more, sorry. It wasn't until DenseNet 201, where I saw kind of like this inaccuracies and F1, so 74% validation accuracy. Okay, so I know at this point that I had to work with maybe DenseNet. I think ResNet is somewhere here as well. Then I tried giving DenseNet, but changing, using the exponential learning rate 1, as well as the NATM optimizer 2. The other one is this EfficientNet, just EfficientNet, no other optimization. That gave me 81 accuracy. Then 201 with 1, 2, and 4, which is the augmentation version 2. So you see I have a 102, I have a DenseNet 1, 2, which is 81%, and but just by adding the version 2 augmentation, I was able to increase it by a little bit, by 0.001. Then I realized, okay, this models actually could keep going on training, so I increased the epochs to 30, and that's where we see a little bit of better performance as expected. So EfficientNet with 1, 2, 9, and 10. So that's pooling, exponential learning rate, NATM, and Noisy Student. Did about 84. ResNet for me did well as well in general, 1, 2, 4, 1, 2, 4, 5, which is the workers. For some reason that did a little bit slightly better for me, and but that wasn't universal, I think. 1, 2, 3 with just ResNet for some reason just overfitted. Then I was capped here at 88% or 88.88 validation accuracy. And that's when I saw on Kaggle online, so people are actually training or continuing to train the CovNet backbone of when they transfer learn. So then I tried that, ResNet 1 and 8. Again, 8 is pre-trained model, trainable equals true. That gave me a 92 accuracy. Now the DenseNet performed a little bit better than ResNet. It gave me 95. And I tried, you can see here different combinations, 1 to 8. 8 is the pre-trained, 1, 8, 1 to 8. What is that? 11, which is weights. I didn't see a difference with weights. the last red one is or before I go to the red one, the purple one is the efficient net one with kind of like all the whistles and the bells, 1, 2, 8, 9, 10, 11, 1, 2, exponential learning rate and atom, pre-trained, noisy student, and weights. For me, that performed the best on the validation set. But what performed the best on the Kaggle competition was the ensemble of this EB7 and 201 with, let's see, just the basic EB7 and 201, no other parameter tuning. Questions about this graph and what it means and how do you interpret it?
So just say it again. So EB7, which is efficient net 7, and DenseNet, the ensemble, with no augmentations and no class weights, perform the best?
Sorry, let me, before I say that, I have more detailed notes here.
Okay.
There you go. Sorry, there was some tuning there. My bad. So this is the ensemble, which used, okay, there you go. Actually, no, I tuned DB7 as well. 1, 2, 8, 9, 10, 11, which is the class one, the weight one. 11 is weight. Oh, sorry. And DenseNet as well, weight was there as well. So 1 is just the learning rate schedule, 2 is NATM, and it was both present. 8 is trainable true. 9 is just efficient net. 10 is noisy student, and 11 is the weights.
Okay, so the ensemble with the tuning was the best.
The ensemble with the tuning, with weights, with NATM was the best.
Okay.
Yeah.
Hey, George, this is Ted. I had a question about the chart. So you kind of show them in increasing performance, but in reality, chronologically speaking, did some of the worst performing ones come after some of the better ones? Are there some experiments you tried that, did worse?
Absolutely, yeah. So this is the index that I tried on. 0 is the first one. 1. So you can see the index, the higher the index, the more chronologically later it appears. So the last was here.
I just wanted to say that because for other people, when they do this and they try things and things actually get worse, I don't want them to be disappointed.
Yeah, look at this 20, right? 20 is pretty late, but it actually performed.
Does that happen to you, Ted? I thought every time I made a change, it improved the model.
Actually, my experience is more often than not, my brilliant ideas not only don't make an improvement, but they actively hurt performance.
It happens.
I have a track here on when I was submitting this on Kaggle, right? So I started with a very basic one, 0.04 nothing, then DenseNet 201, 0.65, and MobileNet 72. But then again, this kind of biased because I only submitted when I had a better performance in the validation set.
George, I have another question along the same line. So is there any pattern, like in terms of maybe model size or, the initial sort of data set it was trained on? If you didn't have, that much time or compute power, was there any other way to figure out which ones would perform best?
Yeah, that's a good one. I don't know. I mean, I would think that the basic deep convolutional ones that have at least a few million parameters, I would expect them to perform relatively well. I know for sure that some of them were much faster to train and some of them were really, really slow to train. For example, MobileNet, because it's optimized for mobile devices, it was the fastest to train. Like the other ones took 20 minutes. This one took probably 5 minutes to train. But yeah, by default, I didn't know, okay, if DenseNet 201 or DenseNet 128, there's so many DenseNet out there. Usually my approach was just take the latest one or the highest capacity one, just because this is a demanding data set.
Yeah, I really like the way you have a lot of the experimentation displayed here, and you collect all the information into a data frame like this. Mm-hmm. A couple of things that I think would add to it even more would be to include, like a quick column containing number of parameters or something, and something about the training time, just so then you could even create other scatter plots where you'd kind of see those trade-offs.
Got it. Yep.
George, how automated was this experimentation? I mean, you have a lot of different experiments there shown. I mean, it looks like some of it was somewhat automated, and it's nice to set it all up and then click a button and then go away and come back in the morning.
Once it wasn't automated in the beginning. The beginning was me trying to figure out. Sorry, here's some echo. Can you mute somebody? In the beginning, it was me trying to figure out new tuning methods. And once I realized that, once I kind of established myself to these tuning methods, then I kind of had a process of, okay, once I change something, run all and just, go grab a cup of coffee or something. So at that point, it was more manageable. I want to go through these other metrics as well, because I'm only showing validation there, but I want to maybe, sorry, I still hear an echo. Is anybody muted? Robert, do you know? So this is us exploring the data frame, but a little bit better or closer. I'm going to skip the 12 epochs one, and you'll see here at most of them. I had a lot of models with 12 epochs, but most of them were in 30 epochs. Let's look at some interesting ones. This is loss and accuracy. Where did it take place by model family? So we had DenseNet, MobileNet exception, and I wanted to track what was the minimum loss. So the lower the better. That's very interesting in this area here. And accuracy, the higher the better. So you can see here as well. But I think this is just for the 12 epoch. Yep. So I'm going to ignore the 12 epoch. Here we go, 30 epochs. Cool. And this is, we're looking at loss and accuracy again. For 30 epochs, I just used DenseNet, EfficientNet, and ResNet. Min loss, I want it as minimum as possible. And accuracy, I want it as high as possible. So you see this one had the best accuracy on the validation. This one had the best performance on the actual computation. And then some other ones are very close here. F1 precision and recall for different models. So again, by model family, I wanted to see if there's a pattern on the model family. And the higher the color, the higher the recall. So you can see this one has the highest recall. And F1 is on the x-axis and precision is on the y-axis. I think this next chart kind of combines all of them. So it has F1, precision, and recall. Oops, sorry. On one chart. And you can see here that DenseNet with different tunings are very high here. Zoom in a little bit. Yeah. Some visual validation. This is just a batch. We got most of them right except for this one. And then my other option, the other tuning I'm doing right now is looking at the ones that I did not classify correctly. So for example, the predicted was 71, class 71, but, or sorry, I predicted 71, but the correct class is 73. I want to focus a little bit on those, take a look at those and see if I can get an intuition on what is common between these failures. Is it something in the background? Is it maybe the contrast, the position of the camera, if there's anything? That's what I had. Let me go to the very beginning which I have the long list of things, make sure I covered everything. So that was a 3D chart. Yep, the other tuning that I'm trying right now is more training data. There's another external data set that increases the training size from 12K to 70,000 images, yep, 68K. I suspect all the top models in the competition are using that. Some other notebooks I've seen uses a lower dimension or resolution image, 224 by 224. I might explore that as well. In the past, we've seen some discrepancies between TF-Keras applications, right, David, if you remember, and Robert, and versus TF-Hub. The same model that is hosted on TF-Keras application performs slightly worse than TF-Hub, so I might explore TF-Hub or this model garden that we saw. Some other notebooks I've seen use this mixed precision, which basically I think quantize a little bit or play a little bit around with the float point operations as you're using the TPUs. The other one is if you want to do some kind of augmentation as you do test, you can do that as well. The other one is, and Dimitri, you shared a link last time, but I'm always interested in model explainability of, can we figure out why a model was incorrectly or correctly labeled? So maybe if we can track somehow, if we're able to identify which parts of the image labeled the rose as rose or a lily as lily, and maybe focusing on the ones that I mislabeled, that'll give me some intuition. There's some data augmentation methods. That paper that I shared with us, this one here is one of them. Maybe I can take a closer look. Yeah, and just asking for your help, just avoiding if this is interesting, feel free to upvote it. Pretty close to, so I crossed the 20 votes. Next one is the 50 votes, and I'll get my first gold medal. Let's go here. So most of the notebooks, most of the competitors don't have a notebook, and most of the participants, very few have, including myself, for obvious reasons, I think. But I just enjoyed learning from each other and communicating with other people here in this competition. I want to thank them as well. Cool. That's all I had for this competition. I will stop sharing and open it for questions until Neil takes over for the next competition.
Can you share the link here in the chat or?
Yep, I'll share it again. Yep. Yeah, I shared at the beginning. I'll share it now. Cool. Let me share screen.
I have a question.
Go for it.
So continuation of
you're coming a little bit choppy, Vladimir. Go for it.
Continuation of
Sorry, maybe go for it.
Continuation of Dmitri's question. So in this case, we're just taking some already designed architectures and methods. How about we just try to design architecture that is suited for our problem? Because not all methods are designed equal, right?
Vladimir, you might need to just can you type it into the chat for us? Can you type it into the chat for us?
All right. Okay. All right. So there is probably network problem. All right. Okay.
George, I think you're muted.
Sorry. I don't know if I understood what he said, but maybe try creating your own network from scratch. Is that what he was asking? I'm not sure. Instead of a pre-trained one. Cool. Well, hopefully we'll get to that in the chat, Vladimir.
So the approach you took, George, of starting with very simple approaches and then building on is something I've seen, like the people who win the contest say that's the best way to go at these things.
Mm-hmm.
And learn as you go and continue to add complexity and and experiment.
That's the only way I knew. I didn't know how else to approach this.
Well, some people try to, they try to, based on other things they've seen people do, they'll implement the most complex thing first. And
oh, I see. No, I always wanted to understand as well what is the impact of each tuning method.
Sure.
Because in many cases it performed the same or even worse. So I wanted to get an intuition of when you use this tuning method versus the other one, what is the impact on F1 and accuracy? Cool. Awesome. Thank you, friends. Neil, would you like to share your screen?
Yes.
Cool.
Give me 1 second here. share screen. Okay, can everybody see my screen?
Yes.
Yes.
Okay, great. All right, well, thanks, George. That's going to be a tough act to follow. Thanks for giving me the opportunity to do this. I haven't presented at one of these before, so I was kind of eager to, I've been involved with these meetups for a long time, and I've been eager to get a little more present with some of it. So with this machine vision, I thought this would be a good one for me because I actually have experience doing some machine vision with some of the work that I do with image classification and object detection. So I offered to present some of the sessions in this Kaggle, and George asked me which ones I wanted to do. So without thinking about it too much, I just kind of glanced over the list, and I saw that there were 2 Kaggle competitions at the end that involved, hey, you can try training on a TPU, and that got me excited because I'm kind of more computer architecture, hardware oriented kind of person, as a lot of you know me. So I thought I haven't actually had a chance to get hands-on with a TPU. So I said, let me do one of those. And so I'm going to be presenting one that's similar to what George did. But I have to say that as I started working on it, I realized I maybe got in a little over my head at first, just because there were a lot of firsts for me in this. There were a lot of new things for me to do. I had not done a Kaggle competition before. I had not, there were a lot of new things that I hadn't done before. I hadn't actually built and trained a model like this before, and I'd actually just implemented them in hardware, but I've never actually built one myself. So there were a lot of new things for me to learn, but I got through it, and it was a really good learning experience for me. So I will go through the experience that I had and how it went. So this is another competition. It's got some similarities. It's an object. It's an image classification. So it's this. In this particular one, we're classifying these cassava leaves, which are commonly grown in Africa, and they're used as a source of food. And but they sometimes get diseased, and since they're widely grown across the continent, and they don't always have access to experts to diagnose the leaves. They're looking for a machine learning model that can classify whether the leaf is healthy or diseased, and if it is diseased, what type of disease does it have? So there's like 5 different classes of one of them is healthy, and the other 4 are different diseases. They never actually tell you what the diseases are. They just have a label 0 through 4. So anyway, there's a big data set that they provide, 21,367 labeled images. And this thing is sponsored by an AI lab. This actually has a prize associated with it, this competition. So they're serious. I think they really want to get the best possible result. So let's see, the data. So they provide, they provide some training images, they provide some validation images, and then you can see the images are provided in 2 forms. There's the actual JPEG images, and then, which you'll see later. They also organize it into these TF records that George was talking about before. It's the same data, it's just organized. You can see there's not that many files because each file has a lot of images in it. And they also have just one test image in this case. So you basically train the thing, and you can test it on one. Of course, you don't know if it was right or wrong. They're just kind of working you through the mechanics of how you do that. Because then when you actually submit the design into the competition, then they substitute this test image with their own secret hidden test images and run it through your inference engine, and they can determine how well you did for judging the competition. So let's see what else. You can see there's a bunch of people already doing pretty well on this. I never didn't even hope that I could seriously compete well in this, but I thought I could see how well I could do since I'm new to this.
So,
and in this particular case, they are, let's see where it says here, the judging criteria. I'm trying to think where they put that. The judging criteria
overview.
Maybe it's back in the overview. Yeah. Okay. No.
Evaluation on the left there.
Oh, thank you. That's what I was looking for. Yep. So the submission has to be in this format. So you have, you know, basically the test data, you run it through the inference engine and you provide an image ID and the label. And in this case, they're evaluating entirely based on categorization accuracy, not the F1 score as was the case for the one that the flower competition that George presented. So let me talk briefly about the TPU. So that's one of the reasons I wanted to work on this one, is because you guys actually get to train on TPUs, and I wanted to see what they actually had. I don't exactly know how Kaggle gets access to these, because it's Google. TPUs are Google chips, and they use them in their data center, and I guess they must have some arrangement with Google. I guess this must be hosted in the, yeah?
Just Kaggle was bought by Google about 2 years ago, and they introduced the TPUs.
Oh, well, that explains everything. Okay, I actually didn't know that. So
they have an inside source.
Okay, well, I guess that should be public information. But anyway, so yeah, so this is obviously hosted in the Google data center then, and the particular board looks kind of like this. So there's like 4 chips, and there's 2 cores per chip, so you get a total of 8 cores. And this looks like it's a PCIe Express kind of card that you can plug into a server. So that's one thing I didn't realize. When you're running on the TPU, you're actually running on a whole different server, a whole different machine that has its own CPU and running with this board in it. So there's some also other TPU specific considerations. This, by the way, there's a link to this page, how to use Kaggle with TPUs. So if anyone wants to try this, read through this. There's a lot of really interesting information. It's a little different. You get 30 free hours per week of TPU time, which is really nice. All right, so let me go to my
quick question, Neil. There was a question in the chat about what the speed up of a TPU versus a GPU was. I didn't know if you had any ideas.
Well, I actually was not able to try it on a GPU. I was curious because strangely, I don't know if you ran into this, George, but you know, you get to choose CPU, GPU, or TPU. So it starts off with CPU, of course, it's just ridiculously slow. And then I tried training with the GPU just to see what would happen, and it actually didn't work at all. It bombs out with a memory it runs out of memory, basically. So maybe it's just specific to this particular exercise that it's got such a large enough data set that it's running out of memory on the GPU. Maybe the TPUs that we're using have more memory. But I guess I probably could have, if I really was that curious, I could have worked a little harder at it, maybe pared down the data set and tried it, but I didn't. So I really don't know. I'd imagine it's a lot faster, because otherwise they wouldn't have bothered to make this available as an option.
Yeah, I accidentally tried training without a TPU, just on CPU, and instead of 1 minute per epoch, it was taking me, I don't know, probably 20 minutes per epoch. Like it was, I knew something was wrong. Like, why in the world it's taking 20 minutes just for one epoch? And
did you try the GPU?
I did not try the GPU. No, I just accidentally tried CPU and TPU for most of my.
I'm surprised it was only 20 to 1. I thought it'd be a lot more than that, actually.
That was just on one epoch ETA. So.
Okay. Yeah. All right. So I'll go to my notebook. So my first goal was to just try to run the notebook in the form that they provided to you, and then I decided, you know, to try to enhance it and try to get better results. But for me, just walking through the exercise was a new thing. So a lot of this is really almost the same as what George presented. So I'll go through those parts really quickly. Do
you mind zooming in just a little bit?
Yeah, sure.
Oh, plus. Thank you.
Is that better?
Thank you.
Okay, so this is just some setup stuff, and then you saw this before. This is setting up so that it actually uses the TPU, and if it successfully sees the TPU, you'll get the 8 cores that we talked about. If you have the TPU mode turned off, then this will come up as a 1, which means it's not running on the TPU. It'll either be the CPU or the GPU. depending upon which one you have. And then there's some, setup variables, pretty basic stuff here. In this case, there's 5 classes. They're just labeled 0 through 4. The image size is the same as what we had in the flowers, 512 by 512. Start off with 25 epochs. And then loading the data is pretty similar again to what you saw before. It's these TF records. We read in an image file and convert it to a floating point. And convert it, reshape it to the right image size. This is the same exactly thing that you saw before. Again, it's reading in the TF record and it's breaking out the fields. If it's labeled, then there's an image and a target. If it's not labeled, then it just has an image and an image name. It returns those values. And this is a routine to actually load the data set. Again, it's exactly the same thing as you saw before. We're reading in the TF records. Since we saw this before, I won't go in any detail here. And this is the test and train split. I just left it at the default here, 0.35 for the test size. And this is just pointing to the path for reading in the TF records. And then there's the augmentations. So the default augmentation here for this classification is just, again, the random left and right flip. By the way, this is the notebook that they give you. I will show you my enhanced notebook when I go over the optimizations I tried to make. Let's see, these are the routines for getting the actual data, the training set, validation set, and the test data set. They're same as what you saw before. In the case of the training data set, we actually augment the data and shuffle the data. I'll also mention one thing I don't think we said before is that this training is being done with just-in-time data augmentation. So what happens is when it reads an image from the data set, it randomly augments it. So that's done on the TPU. Actually, it's done on I believe the CPU part of the TPU. So you don't really get any penalty for it. It's running sort of on the CPU piece of it, not the accelerator board. And so the nice thing about this is you don't have to actually store the augmented images. They're just augmented on the fly as the training is done. And each time you go through an epoch, the augmentation will be potentially different. That's how you get the variety of data. All right, so here we have 13,000 so training images, 8,000 validation images, and as I mentioned before, there's only one test image in this case. And then this is, again, the same thing that you saw before. This is just showing the format of the data, the shapes of the data. So we have the batch size of 128, and the image is 512 by 512, and it's a color, so we have 3. And this is just showing some the first 128 training samples and the first 128 validation samples, and then the test ID of the test.
To clarify, Neil, you only have one test set because this is an actual competition, right? So they're not giving you the other answers. So it's your job to predict the full.
Yes, that's right. You have to predict it. But I thought in yours they gave you more.
Yeah, I'm saying this is just a sample notebook. I think in the competition itself you might have. No, you might. You definitely have.
Yeah, no, you're right. In the competition, they throw like something like another 15,000 samples at it.
Yeah.
So this is just, I think the only reason you have this is just to test the mechanics that you can read and do inference on a test data set. And then when you actually run it through the Kaggle competition, they substitute in their own.
Yep.
Okay, so this is, again, the same as, I think this is the same as, oh, this is just for displaying the pictures on the screen, just so you can see what they look like. These are various, I think, similar to what you saw before with George. So when you run this, you see here's what some of the leaves look like. So this is the sample of training images, and the next one is a sample of validation images, and then this last one here is the test image, which we don't know what it is. By the way, these are like randomly displayed. So if you run the notebook again, you get a different set of images each time. Okay, learning schedule. So I didn't do anything fancy here. This is straight out of the box of what they gave you. Not like what George had, but you know, there's a, it is using a scheduler. So there's an initial learning rate and then it decays over time. And it is using the Atom optimizer. I do play around with the learning rate a little bit, but that's about it. And then the model, here's the model. So the default model here is ResNet 50. I think the same as before, using the ImageNet weights. And the default is to have the base of the model to be not trainable. So that's what this is doing. And then we add a head to the model. And that's what's happening in here. So, you know, this is the whole model here. We have a batch normalization. We have the, this image adjust layer is to get the resolution and everything right. The base model is the ResNet 50. And then we are using the global average pooling here, same as before, which works really well. It seems to work really well. And then in this case, we have 2 dense layers. I think George has only had 1. This one has 2 dense layers. The first one has 8 nodes, and the second one has the number of classes, which is 5 in this case, with the soft ReLU and the softmax. And then for the metrics, we have the, since it's a classification, we have the categorical cross entropy for the loss and the categorical accuracy for the metrics. And this is where we actually load the model. And
I can make a comment, Neil. That pre-processing step, it doesn't exist for every model, that image adjust layer they have, but for some of them it exists, and it makes a huge difference. For the ones that I used, I didn't need it, but for some other ones, like ResNet 50, for example, I think you need it, and it makes a big difference.
This one here?
Yeah.
Okay. Good to know.
Pre-process input, yeah.
Yeah, I didn't touch this at all. I figured it's working. So, okay. And then you train the model. So this is again right out of the box. It's 25 epochs. You can see, run the training. You can see it. It's pretty fast. Each time it goes through, the first one's a little slower, and then the subsequent ones take about 36 seconds for each one. There's a total of 25 epochs, and there's 104 batches per epoch. So you can see how fast it is. And then we get the results of the test of the training. This actually shows you the some information about the model. This is the summary of the model. You can see how many parameters there are, and you can see how many of them were, in this case, not that many of them are actually trainable, because we use the existing base of the ResNet 50 trained already. And then this actually shows us our learning curves. So again, out of the box, we can see how it did. You know, 60% or so. It gets there and it climbs slowly, and it doesn't really get that. I didn't run this any longer than this because I figured they want you to try to do better. I already saw the leaderboard and it was much better than this. So this is just getting started. And then finally, the actual inference step. So this is where it actually takes the test data and it runs it, and it computes a prediction. It predicted class 3 in this case. And then you have to, for Kaggle, you have to create a file, a submission file in this format. So here's the file that it created. It's a CSV file. This is the label and then the prediction. So that's where we started. Once I got through that, I said, okay, well, that's pretty good for me, but let me see if I can try to do a little bit better than that. So let's see here. Where's my improved notebook? Let me open that one up. A second here. Okay. Actually, what I'm going to do is pull up another Word document that I created that has a bunch of results. So this is what you just saw. This is where we started, the baseline. And so I thought, okay, well, what can I do to try to improve this? So my first thought was to try to, I had a hint from George. He had already mentioned that he had gotten better results by training the full model rather than using the pre-trained weight. So I decided, well, I was a little afraid it would be really slow, but I decided to go for it anyway. So I trained the full model basically still using ResNet 50. All I did was just allow all the weights to be trained instead of just the head. And right away it got like way better. You can see what it looks like here. It's the actual training data, it was inclined pretty smoothly. The validation data kind of a little choppy, but still kind of going in the right direction. So that was right off was kind of better than I thought. And actually it wasn't that slow. I mean, it maybe instead of taking like 36 seconds per epoch, it maybe took like, 45 or 50 seconds, like not horrible at all. I was kind of surprised considering how many more weights there were to train. So I was like, okay, I'm going to go with this. So then the next thing I experimented with was I didn't try all the full multitude of models that George tried, but I just picked a big one that's supposed to be pretty good, Inception V3. And that improved things even more, actually. You can see one of the notable improvements was that the validation data climbs a lot more smoothly and is less choppy here. So that was already I'm getting up to like 80% accuracy from where we started. And since it was still climbing, I decided to try running it for 100 epochs instead of 25 to see how well it would do. And you can see it really, we start to overfit the data. The test data really does a really good job of getting close to 100%. And the validation data really maxes out pretty shortly after the 25 epochs. So clearly we got to try to improve improve the situation there. So I thought, well, maybe we need to improve the variety of the data, or introduce some degree of regularization to see if any of that would help here. I didn't play around so much with other models yet at this point. So then the next thing I did was I thought I'd try to make, before I introduce regularization, I thought let's try to make the model itself a little more capable without changing the inception. So I just increased the first dense layer. So instead of having 8 nodes, I made it 32 nodes. I thought, well, let's make it a little bigger and see if that would help. And it made a small difference. I can't say anything dramatic there. I left it because it wasn't that much slower, but just something to experiment with. And then I added more augmentation. At this point, what I did is, I'm going to go back to my notebook now for a second. I'm going to just show you, catch up to where we are. So the changes that I made, let's see. Okay, the augmentations I added, we started off with a random left-right. So I figured for this one, I think we could do up-down because it seemed like the leaves were in kind of random orientations anyway. And then I added a rotation to it, figured what the heck, random rotation. And then I varied the brightness a little bit. I also experimented, I kind of left this one out, but I experimented with contrast. So these are basic out-of-the-box augmentations that they offer. And they, I think I showed you the results here for the augmentations. It did get better in terms of the accuracy got a little bit better, but maybe more importantly, the overfitting situation improved somewhat by doing this. I don't see it diverging as much, which is kind of what I was hoping for. I was hoping that it would be able to generalize on the data a little bit better rather than memorizing the data by giving it a richer set of data. Let's see, going through here, I can also show you the changes I made to the code in this updated version. Yeah, so here's where I use the, showing here. I'm using the Inception V3 here instead of ResNet 50. And one thing I had to do, I don't know why, but I found that if I, at least in the case of Inception V3, if I made all the weights trainable, it never got off. It like kind of got nowhere with the training. Basically, I would get a number for the, I would get a not a number for the loss. And so but when I turned off the training on the Inception, that I didn't have that problem. So I experimented with just going through like the layers within Inception V3, and I found, just sort of experimentally, I don't know why, and if I make the first 5 layers of Inception not trainable and I leave all the rest of them trainable, then it overcame that problem. So I figured the first 5 layers are pretty easy, basic features that it's learning. So I figured it probably wouldn't make much of a difference, and it didn't. So thought I'd mention that.
What was the problem you're trying to overcome, Neil?
The problem was that when I did the training, I would see this, the loss number would be not a number, NaN.
Oh, I see.
It's like it was dividing by 0 somewhere or something. I don't know why. I Googled, I tried to find information on it. There's a lot of things that can possibly cause that. And I figured I just experimented until I got past it, but there's probably a better way to deal with it than what I did. But
was your learning rate really large or non-changing, or what?
It was, I left it at the default. It was like 1 × 10⁻⁵. I guess I could have played with that too. But even what's weird is even in the first, right from the get-go, even in the first epic, it was not a number, which surprised me a little bit. I also thought that it would, because in the first epic, it's not updating any of the weights yet. So I thought that the, if I started off with the actual ImageNet weights. So it's starting with real weights. It's not starting from nothing. So it should do the first pass of the training and give like a reasonable loss number. And it wasn't for some reason. I never figured out why.
Is there any reason it might compute an infinite gradient there? That's the only reason I could think that something like that might happen. But I haven't encountered it.
No, I mean, I was thinking along those lines too, but I couldn't think of a reason. Anyway.
Maybe have a pre-processing step that you need to set up like you did for ResNet.
Well, yeah, I mean, I left all of that part the same, so it still has the image adjust layer and the.
Sure, but that is different for the 2 different models.
Maybe that's what it is. Maybe I needed to use a different pre-processing step for this one. That's something else I can experiment with. So yeah, so I changed the Inception V3. I actually, later on, I'll show you, I added some dropout in a couple of places. I also changed the dense layer to 32, as I mentioned before. So these are the kind of changes that I made. So so then with this one, it got, a little bit better. And then after that, what did I do? I added even more augmentation. I think the first pass, I just did the flipping and the rotation. And then later I added the, this is where I add the dropout. That's what it is. Here I had no dropout. Here I added dropout. So I wanted to see if that would make a difference with some kind of regularization would help. And it didn't, it helped a little. I don't think it really, at this point, the changes I'm seeing are kind of, smaller. So I need to probably do something a little more dramatic to get better results. And I didn't hit upon that yet. Maybe a different model, or maybe adding more training data, or maybe, maybe some other types of, actually what I was really thinking would help a lot here. Since this is different from this is a disease classification. It's not an object detection. Like, we're not like trying to determine what kind of leaf it is or what kind of flower it is. We're trying to determine how diseased is the flower, is the leaf. So I thought maybe there's something about the texture of the leaf or other properties of the leaf that might be useful features. So I didn't get very far. I started looking into like other ways I could extract features to use in this model. I started looking at some texture feature extraction and some others, and I didn't get far enough along I ran out of time to try. I'm going to do that next. I'm wondering if I do that, if that would give this model a little more information to learn on how to classify these diseases.
That's more like a traditional image processing, or is that like a deep learning model that does?
I'm thinking maybe some traditional techniques.
Okay.
I don't know. There was one talk that someone gave on some like using wavelets to determine, to classify textures. I was thinking about looking back at that and see if something like that could be applied here. Again, there's a lot to do, so I'm just trying to get through it. Let's see what else. Let's see. Okay. This is wrong. I did not. At one point, I tried adding some cropping, and it didn't really make a big difference. I took it out. Last thing I did is I just increased the learning rate, because I discovered that, you know, this is pretty smooth. It's not choppy. It's doing a really good job of learning pretty quickly. Surprising, especially considering that I'm training on all the weights, you know, although it is starting with the ImageNet weights. But so I thought, well, maybe that'll, you know, I just wanted to see what would happen. So yeah, it actually learns very quickly. It doesn't take that many epochs to get up to this like 80%, and then, but it still kind of maxes out. So this is about as best as I was able to get. I got about 85% accuracy on the validation data. So let's see, back to my notebook. What happened? Oh yeah, somehow I ended up all the way at the top. Okay, so last thing I'll talk about here is the actual submission. This is not the final one I ended up with. Oh yeah, so the final prediction here was a 4. Now, when you actually do a submission, I discovered some things that are particular to the TPU. So if any of you guys are working with the TPU, you kind of need to be aware of this. I guess you must have run into this too, George, is that, well, first of all, you don't need all, like in this notebook, you don't need most of the stuff here for the actual submission. You just need the inferencing piece of it. And they don't give you I didn't see that they gave you anything canned for that. So I had to create another notebook, you know, copy this notebook to an inferencing notebook, and then take out all the stuff that was related to training and just leave the inferencing part. So then all it does is read the test data, run it through the model, and then generate this submission file. And the other thing is you have to have the TPU turned off, and you also have to have the internet connection turned off. So there's a place here where you can see where that is. Settings, and it
was right there on the settings.
Yeah, so under here you can choose, you saw this before, the accelerator, you choose GPU or TPU or none. You have to have it set to none, because the validate, when they run it through the Kaggle competition, they don't have a TPU set up there, or they don't use a TPU.
You can have it on TPU, right?
I had it on TPU for the actual training, but then the inference model, I have to have it set to none, and you have to have this internet turned off, and then you can submit that into to Kaggle. So that's something. And then the other thing.
Go ahead. Go ahead.
The other thing. Oh no! Why don't you ask your question? This is a good.
I was going to say, I think you have to have the TPU turned off, but I believe they do allow GPU for the inference part.
Okay, that
GPU
might be.
GPU, but
that might be. But yeah, you have to have the TPU turned off. And then the other. So that's, you can't have any TPU stuff in this notebook that you submit, because if you do, it won't work because they don't have a TPU. Also. You have to, the model itself, because we're training the model on a TPU, but we're doing inference on a machine that doesn't have a TPU, you actually have to kind of export the model. You can't, you basically need to get the model from one notebook to another notebook. So there's instructions in here on how to do that. Where did I have that? So, oh God, I had that in the second. Actually, it's in there's a link to it down here. Let me find it. Bear with me. Thought I had it open in a window.
So you're submitting a notebook and a CSV file?
No, you just submit a notebook.
Oh, I see.
So
this is supposed to run on a phone, right? On a smartphone.
Well,
in the end.
That I would infer that that's what they would like to do, given the use case of where this is being used in rural parts of Africa and stuff. We never actually do that here. All right, so here's what they tell you have to do. So you actually have to save the model. So after you've trained the model, you have to save it to a file. Okay, and then when you actually do the inference, you have to read the model back. And in order to get the model from one notebook to the other notebook, you have to go through a couple of acrobatics. You actually have to create a data set in Kaggle. Let me see if I have mine handy. Let me go to another window here. Data. My data. Okay, so Neil's cassava leaf disease inference. So if we look at my data, you know, this is the data that was exported from my first notebook. So there's the model that I trained on. It also puts the submission.csv, which is that one test image but it doesn't really need that here. It just needs the model.h5. And then in the inference notebook, you actually have to read that back. I'll show you my inference notebook that I created. And I don't think you normally have to do this. I think this is specifically because you have TPUs here and the training has to be done in one notebook and the inference has to be done in another. And maybe they'll make this easier at some point, but if you want to do TPUs, you got to deal with this.
I think so, yeah. I did this manually. Did you do this with some kind of Kaggle library? Did you create this data set through a Kaggle library or manually?
No, what I did is, it's actually really easy. You just, let's see, how did I do it? Oh no, I guess you could say it was manual. Basically, you go to the data, and then there's somewhere in here you can, I guess I have to get out of this. You have to say new data set, sure, right? And then, you know, you have different ways to get data. You can drag and drop. You can get it from a URL. Yeah, or you can get it from a notebook, right? So you go here and you find public notebooks or your notebook. So then I go to my notebook, right? And I didn't mean to click on that. But basically, yeah, you can import the data from an existing notebook. So the flow goes like this, right? You have your training notebook, you do the training, it saves the outputs to these files. Then you go and you create a data set where you actually import the data from your notebook, right? And then now it's saved into a data set. And then when you go to your inferencing model, your inferencing notebook rather. So here's my notebooks. I'm gonna go to, let's go down here. This one here, inference. Okay, yeah, this is the one that I created. So this has its own data associated with it. I guess I have to edit it to see it. And then, so here's the data sources, right? So here's their data, the cassava leaf disease, and then here's Neil's. So inside here is the model that I actually saved into the data set. And then inside here, I actually have to then, I'm no longer training here. I've removed all of that stuff. I just, a lot of this stuff is just commented out. And
is this what you were saying, that you can use GPU, or did you have to use CPU?
You know what, you're right. I had it set to GPU. Yeah.
Oh, okay. It's faster, right?
Yeah, yeah. So here's where I load the model, right? So I load the model from, it's this model.h5 from this data set, which is the data set that I saved. So anyway, it's kind of a manual process. Maybe there's a way to automate it, but this is what I had to do to get it to work. Did you have to do anything like this, George?
So this is unique to this competition because they are targeting, you know, edge devices like phones. So a lot of ones you don't do this.
And Neil,
Right.
Neil, I was going to ask you, do you have the option to export it into TF Lite? Because that fixes the model and allows you to run the optimizations on it. I don't know if that would make it any more accurate, but it would definitely make it faster.
Yeah, I think you can do any. I mean, this is full blown, you know, TensorFlow here, so you can do that. You can do anything you want, really.
Because you see what I'm saying. If you open up the base model, you haven't done any optimizations on it. Of the deployment optimizations, like you haven't, you know, pruned.
Oh, you mean like optimizations for running it in light hardware? You mean like pruning and quantization?
Yeah.
And stuff? Yeah. No, none of that is being done here. This is just straight all, you know, full blown TensorFlow, Keras, floating point models.
Did you try any of that to see if it would influence the accuracy?
No, I haven't tried any of that. That wasn't. I don't think that was what the exercise here was. Just to try to run on train on TPUs. So everything here is TPUs and GPUs. You got some pretty, but yet that's a good point though, because I mean, I would infer from the nature of this competition that they would like you to ultimately go to a kind of an edge device, because again, the use case for this thing is you're in Africa, trying to use this in the field, right? And you're not going to have a data center available there necessarily. You may not have a good internet connection, or you may. So yeah, that would be a nice follow-on exercise. I think would be to, if once you get a model that works really well, would be to try to, kind of optimize it for an edge device, like a mobile phone or one of the other many other edge devices we've talked about.
Yeah, the other thing I was just asking, because I didn't know, was since as part of that process you would be forcing any small weights to zeros, would that potentially improve the accuracy?
I would think it would hurt the accuracy, right? Anytime you distort the weights or anything in the model. I mean, I think the idea there is that you're trying to minimize the effect on accuracy while at the same time making the model a lot smaller, so that it can run on a lightweight device. So no, I would think that it would not improve the accuracy if you did anything like that.
Are you thinking about quantization or
I think he's talking about quantization.
Oh, Stephen. Okay.
Is that right, Steve?
Yeah. Well, there's there's a whole package. There's a whole package in there with the quantization, right?
Yeah.
I think there's.
Well, there wasn't anything like that for this competition, but.
No. I'm just saying, as a wild experiment, did you try doing something like that to see if like maybe you were getting noisy results, and that your accuracy would actually go up?
I mean, I would like to try that, but I would actually expect it to go down.
I've seen papers where they reduce the model weights by some ridiculous number, like 90% or something, and that slightly decreased the performance, but the amount of weight is like reduced significantly.
Yeah, absolutely.
I've seen that in NLP. I don't know if I've seen that in computer vision though models. I don't know if anybody.
No, they're widely used in computer vision models too. Absolutely.
Like one of my models had like 64 million parameters. Another one had 18 million parameters. I'm pretty sure you can maybe shrink them a little bit, but lower the accuracy by a tiny portion.
There's one called like SqueezeNet that I think does that. Gets it really small and gets decent performance. Yeah, they're basically a couple of techniques are replace weights that are close to zero with zero, so you don't have to compute them at all, or you have you can actually completely remove weights that way. And then another thing that I've seen papers on is sorry about that. I've seen papers on like training, like co-training. So like what you're doing is you do this iterative process where you first do your training with floating point, right? And then you go and you do some pruning and quantization of the weights, and that hurts the performance a little bit. And then you go back and you like train again, right? You just pick up where you left off and you train again, and it learns how to do better with those with those weights frozen to zero, right? And then you may go through a couple of iterations of that, and you actually get better accuracy if you do like so it's sort of like a flow where you have a co-training and training and optimization sort of together, if that makes sense.
Hey Neil, this is Ted. I just wanted to go back to the whole issue about having to do submissions and whatnot. So this competition that you're in is a live money competition. And so for that, Kaggle has to run your notebook against both the public and the private test sets. And so in particular, when they run it on the private, you have to have internet off so that there's no possibility that your kernel could leak information back to you. Okay. In addition to that, they're scoring all these notebooks. They don't want to use expensive TPUs TPUs just for the scoring. So that's why they force you to turn TPU off on your submissions. But the way it works is when you submit, it's actually running your notebook twice. It's running it once on the public test set, it's running once on the private test set. And that's why they have those restrictions, just because they're trying to make this manageable.
Oh, that makes sense. Absolutely. Yeah. I mean, they want to make this you know, completely fair. They don't want people to cheat. They want the results to have integrity. I had one disappointing thing that I came across so I did actually do a submission of once I worked through the mechanics of the submissions, let's see, I don't know what happened to so I only got a pretty bad score, 0.72. I had errors on the first couple because there was a mistake in the format that I had to fix. And then I got 0.728, even though when I ran my own validation data, I got more like, 85%. So I don't know what happened there. Theoretically, the data, in their test set should have been, similar to the validation data. I don't know. Maybe I did something wrong. Maybe I had, kind of a pilot error of some sort, but it didn't. I didn't spend a lot of time doing submissions because it took me a while just to figure out how to do a submission. But
I'm not 100% convinced that public score is just based on the test data, though. I think it's also a mixture of a private and public data. Maybe in the overview it tells you exactly how.
George, it should just be the public test set, but I don't know. They might have done something new and different on this one. Generally speaking, Neil, you have to be careful that, for example, when you do test and train, you may need to do stratified sampling, and then I don't think you did, but when people start really trying to squeeze stuff out of these models, sometimes people accidentally overfit validation. And so they're not really generalizing anymore. They're just overfitting on the validation. So those are the kinds of issues that people generally have where their internal scores are not matching when you submit. So that's actually one of the first lessons I learned on Kaggle is keep working until your validation score matches the public leaderboard, and then you can trust your training is actually, has the right goal in mind.
Yeah. So the public leaderboard is the real validation test set, really.
And every now and then the public data set doesn't match the private data set. You'll see stuff on the discussion boards where people are saying, like, we're really concerned that we're trying to validate against these public scores and we're going to run into problems. That that they'll talk about like a big shakeup, because if you don't really know what the distribution looks like, then you don't know what your goal is. And if I see that kind of discussion, then I will avoid a competition, because you could spend a lot of effort and find out that just by pure luck, somebody did better than you because, fluky the way the hidden test set looked.
Yeah, there's also some amount of randomness to it too, right? I mean, it's a pretty big test set, so hopefully it kind of averages to the mean for the most part. But there is some amount of randomness to how the results are going to come out a little bit.
I've been impressed that the degree to which these top performing data scientists, at the end of 2 months, when the hidden results come out, they will only move up or down 1 or 2 places, because they have effectively validated, and so they know that basically their local validation scores are accurate. And as long as the hidden test set matches the public test set, then they're able to very extensively make sure they're not overfitting to some wrong goal.
Neil, I have a question. I'm just trying to figure out if the TPU quota is large enough. So how much did you spend? Like how much time this whole exercise took in terms of your TPU hours?
I used a lot of TPU hours.
That's a weekly, right? You said it's 30 hours per week, right?
Yeah. I didn't use, I used a little bit the first week, just, getting my hands dirty, but I did, most of the, I did, most of the training, in the last week, and it was, I didn't use all 30 hours. I probably used about, 20 hours, maybe 20, 25 hours somewhere. I was getting, but I was pretty satisfied with I was pretty satisfied that I had something reasonable to present for this meetup, by the time I got to about 15 hours. So anything above that, I wanted to make sure I wasn't going to run out of TPU time, but yeah, no, you can go through it. You can definitely go through it, especially if you do, like, I guess the kind of stuff that George did with automating it is a good idea if you want to try to make the most out of your TPU time. You don't want to have to redo stuff over and over again. And, he was also clever with early stopping. If you can early stop, that'll save some TPU time. It's really
this early stop and kick thing.
It's really nice that they offer these for free. I mean, it's it's pretty they're pretty fast. So you don't normally get access to something like this unless you're Google, right? So
you can use them on Collab as well, which is another Google product. But there, it's also limited. So.
Well, how much time do you get on Collab?
I haven't looked at the free version in a while because I pay, but I think that it's not limited by the number of hours per week. It's how much a single run can go. So George, do you remember how long it can run before it times out? It's like
a Collab Pro, right?
Yeah, I have the program. I've forgotten now. It's like 12 hours.
12 hours. Yeah, 12 hours.
Yeah.
And they do have a quota, David. So if you overuse it during a week, they will cut you off.
Okay.
Do you know what it is? Happened to me just a week ago. Yeah.
Okay.
They cut me off. Yeah.
How long is that one?
Say again?
What's the total weekly allotment?
I don't know. They don't have a quota.
Oh, okay.
I was just running, a few models in parallel, and that happened to me the first time. They cut the TPU GPU access.
Okay. Yeah, I think as I remember, people were getting around it before they had that. They were so you'd only run for 12 hours and it would cut you out, but they would just save the model weights, to a file and then get a new session going and start again. So it was sort of like free TPUs for a few weeks there, if I recall.
Yeah, and also on Collab, they wouldn't allow me to run a really large model. So GPUs would actually.
Uh-oh. I lost him.
Collab cut him off. So that 12 hours, is that per instance or per account per day? Like, can you have 3 Collab tabs open?
Good question. I don't know. It's session based or something.
A question to all the users. Have you found any way to profile the activity on the TPUs? So in other words, how busy are they? Just like you can run CPU stats on a.
Yeah, if you open it, Neil, can you open up your notebook and show?
Yeah.
At the very top there, there's that.
Gotta find the one that's.
Yeah.
Yeah. Where is it up? It's up here somewhere.
See those 3 dots there, or just click on where it says like CPU.
It says draft session
on the left. I mean, up a little further up. Yeah, right up in there. Where you're stop the session.
Stop the session. I'm sorry, I don't see
where it says draft session. There's a green button there.
Just you see my cursor?
A little to your left, Neil. A little to your left.
This one?
Just click on where it says CPU.
Oh, yeah, there it is. Okay.
So if you had the TPU, it would show you here how much percentage of the TPU is being used and all that. It doesn't have like graphs or anything. It's got just the live value.
I'm hoping there's a library, right? Because there's all libraries in TPU. Maybe you can manually track the usage.
Yeah, I haven't seen any notebooks where anybody has done that. And in particular, I've had notebooks where I had error messages, the TPU crashed.
Oh, really?
And complete mystery. Don't even get an error message. Just my notebook would just say, there doesn't appear to be a TPU connected to your session. Like, wow, okay.
At the moment, there is not. I don't know what's going on.
Yeah, so that's one of the things that I found very hard is yes, they have more memory, so you can run bigger batches, and maybe it's 3 times faster than GPU, but yeah, it's hard to monitor. So I haven't seen anything where anybody else has said they've done it on Kaggle, Stephen.
One other question. Is it possible to step into the code to see what's actually running on the TPU?
Good question.
I don't think you can, but what do you mean by step into
What do you
the
mean?
code?
Well, I mean, when you're looking at the code here, that's not the code that's actually running on the TPU. There are subclasses here, and you can step into the subclasses using a tool like Visual Studio, and so you can see what's.
I think what's happening here is that, as I mentioned before, the TPU is an accelerator card that plugs into it, some kind of a server, like, machine, probably an x86 class processor that's connected over a bus, a PCIe bus, right?
Yes.
And so this code, like the Python code is running on the CPU, all right? But anytime you do anything that involves the neural network inferencing or training, it's going to call libraries that then invoke the TPU at that point. Now that's all under the hood. You don't get to see, I can kind of guess which steps here call out the,
Yeah, Neil, that's what I was referring to. So since they're bindings on that Python code, in some cases, I know Google originally didn't let you do it. They wouldn't let you step into the code, but you could go into debug mode and step into the code. It's just like any place that says import, you're bringing in a lot of code, but you don't see it because you haven't stepped into it.
Yeah, I don't know if you get that kind of fine level debugging granularity here in this.
Okay, that was only my only question.
So specifically, I don't think you can do it on a Kaggle notebook. And just so you guys know, I'm pretty sure, Neil, these TPUs are actually network attached. So they're not even physically on your box.
Yeah, I don't know how they coordinate it because it's definitely a PCIe bus that's connecting the CPU to the GPU. So I'd imagine you're running on that. Sorry about that. I'd imagine you're running on that particular CPU, but yeah, I mean, you're going over a network, so they must have, the Kaggle machine that you're on, and then the machine that's in the TPU data center, and somehow they're coordinating. Because I think when you switch this here when you switch the accelerator from none to TPU, there's something going on there because they already tell you, like, if you're in the middle of running, I'm gonna not do it. If you're like running in the middle of running a notebook and you're like halfway through running a notebook, and then you switch from like CPU to GPU or to TPU, you can't continue where you left off. You've got to reset and start the notebook from the beginning again. So it's losing all of its state. So I think you're like literally moving to another machine when you do that. Somehow it does that seamlessly.
Yeah, but one of the big differences between GPU and TPU is a GPU is physically attached, like you were saying. And so when you say, I want GPU acceleration, you're running on a physical different box that has a GPU versus one that doesn't. And so, like, somebody early on asked George if he was worried about his quota. So if you were on GPU, that whole time that you're in edit, it's using your quota unless you physically stop the session. On TPU, it actually, you can see that your notebook ran for an hour, but you only used 45 minutes of TPU.
Oh, I see.
Until it hits that TPU connect, it doesn't actually even use TPU.
Oh, interesting. Yeah, I don't know how they do that. Yeah, so what you're saying is they're sharing actual TPU resources across different machines.
Yep.
Yeah.
So that helps because there's limited numbers of TPUs, so that helps. But yes, it does mean that I can't even imagine. It's just that much harder for you to potentially debug or look at, like if you want to see if you're fully utilized, right? Am I do I have enough data? Is my data pipeline fast enough to keep the TPU, 100%, right? It's just that much harder to see these things because it's totally abstracted away via this network connection.
Yeah, there's definitely a lot of things that have to be in place to get the most utilization out of the TPUs. They pretty much tell you that, you've got to have things in this TF record format, and you've got to have the data actually in the Google Cloud, as you mentioned, and you've got to have the batch size set certain ways, and then there's basically a scheduler that kind of in real time feeds the data into the TPUs as they become available and tries to keep them all busy. There's 8 cores running it in parallel. So it's definitely, it's fast, so it's got to keep up.
So unless you have the data in the TF record format, it won't be running.
They say that you have to have it in TF record format to run it on TPU.
Oh, I don't know if that's true. I think it won't run very efficiently.
Or it won't run efficiently. Maybe that's what it is.
Just any data set, right? TF data set from whatever source it's fed. It's supposed to work, I think.
Yeah, the key is the underlying data needs to be on the Google Cloud service, right? It has to be the same place the TPUs are.
Yeah, they talk about it here. If you guys want to read in more detail, it's in this link. Because TPUs are very fast, many models end up with a data bottleneck. So organize the data, reasonably large files, so that these TF records are large files that have collections of data. They talk about.
There you can see it says their usual container format is TF records, but they don't have to be. They're just the most efficient way for it to read.
I see.
But they need to be on the GCS.
I had 2 questions if nobody else has any other questions. First, I want to go to the pre-processing. What did you mean by that, David, when you were talking about pre-processing?
So some models, as you saw, have they put in a pre-process input function that prepares the image data in a certain format that the model needs. And all I was trying, I maybe didn't word it right, but I was trying to say, they put that in as a layer in the model. Oh. And so if you're going to be doing inference, right, and all your images have to be in a certain process. So you've either got to know how to do that outside the model or you use this in the model. Most of the time you would want to put this stuff in that data set preparation, just like you do with the rest of your manipulations of the images to get them ready, like the normalization and all that other stuff. But if you're going to do inference, maybe it's, these TPUs are so fast, it's nice to have it as a model layer, right? The other thing I would say though is make sure you know what's going on under the hood with those pre-processing, that input preparation, because you don't want to do the same thing you may be doing the same thing in your data set. So you might be doing a normalization step in your data set that you don't need to do because the model is going to do that anyway. So just be aware of what it's doing.
So to be aware, you have to
I think all they're doing here, I don't know what this pre-process input, ResNet 50.preprocess input and input shape. So it looks like it's, well, at least one of the things it's doing is it's reshaping the data to this size, if it's not this size. I may be doing other things too, I don't know.
So I know that one in particular does some things like it switches it from channels last, I think, to channels first. So it does more than just reshape the data. And I think some of them do scaling, some they do different things.
So to see what's going on, you actually have to look at the code. Is that what you're saying, David?
Yeah, just most of these things are available. These are all through TensorFlow, so you can go into GitHub and see what actually is doing in the method itself. Most of the time you won't get hurt. I mean, if you scaled it twice to the same scale, it doesn't matter, right? But it's good to know what it's doing, I think.
Yeah, but if you're like swapping colors or something, that's going to mess you up.
Then and it's expecting it one way or the other way.
The other question is related to the training and validation set. So I noticed for this competition, you actually only have a training and a test set. And you do random train test split, which you use for validation.
Yeah, so this just has one, sorry, you're right. This just has one training set and I have to split it into test and validation.
So the actual competition only has training and test.
Yeah, you're right. You're right. I might have said otherwise earlier. So no, you're right.
I'm trying to understand, because every time you run it, that train test split, basically a validation data set will be random, will be different. So
That's right.
Your performance there might be slightly different, even for the same model on the competition leaderboard.
It's, in the train test split, you can set a random state to a seed.
Oh, I see.
And keep it be the same if you want to get consistent results.
Oh,
if that's your goal.
That's maybe what you should do, so that at least you're comparing your model against the same validation set.
They also, somewhere in here, I'm trying to find it. Somewhere in here, they also recommend trying cross-validation, which I haven't done, but that would be another thing to try to maybe get better performance. I can't find it.
Yeah, Neil, that's going to be my next comment, is that if you continue to find that your local validation does not match your public test set scores, I would try adding cross-validation to see if that helps.
Yep. Yep, makes sense.
I hate doing cross-validation, partly because of the complexity, but partly just because if I do five-fold cross-validation, it basically means that I'm using, it takes 5 times as long to train, and I'm using up my quota of GPU or TPU 5 times faster.
Yeah.
Yeah, I would use your first approach to make, as you said, Ted, make sure when you do the train test split, you do stratification so that you get a good distribution, and then maybe you won't need to do that cross-validation work, see these splits.
But later on in the competition, if you have pretty good performance and now you actually are trying to squeeze out, that 1/10%, that 0.02%, you don't know if a model did better or not unless you have really good cross-validation, because you're just going to have random fluctuations when you're sort of that many decimal points out.
Yeah, I mean, if you look at the leaderboard, you see that like the people in the top of the leaderboard are like, they're right next, they're like really close. I mean, it's neck and neck, so I'd imagine it comes down to random chance who gets in first place at that point.
So do you think the validation set they figured out somehow that it's very representative of what Kaggle uses in the backend to test, to give you a score?
Are you asking me, George?
Yeah.
No, I'm saying that you have to do cross-validation to get an accurate estimate of your model's metrics. Otherwise, like when you're doing this initially and you're at 80% accuracy, you don't care if that you're off by 0.1%, 0.3%, it's 80%, right? But by the time you're at 99 point something percent, you need a super accurate validation score to know whether you made progress or that thing that you what we talked about before, whether that thing you tried actually made it worse.
Got it.
And if everything rounds to 99.1, then you can't know if you're moving forward or backwards.
And what are some good approaches to actually get a good validation?
So like, for example, you might even go all the way up to 10-fold cross-validation.
Okay.
Ted, if I just do as a first step, if I have the test train split be random, right? And I just run, I guess you're sort of doing cross-validation at a small level if you do that. I mean, if you run it one time and then run it another time, and since it's random, you're getting a different split, and you can see how much it varies. If it's not varying a lot, then that's pretty good.
Yeah, I mean, you actually have better statistical properties if you use 5-fold cross-validation, but if you ran it 5 times with different random seeds, you could see what the spread of your metrics is.
Yeah.
How consistent or how much they fluctuate. And so, for example, if you were between 80 and 80.5 every time, then you could have a certain level of confidence that that's what your true performance is, right?
Yeah.
But statistically, cross-validation does a little bit better because you're not bootstrapping, you're actually using every
combination,
every row in a different, in a different validation set or whatever. But in this case, yes, I think David's right. First thing is just do stratified sampling.
Yeah.
And that'll probably, that's probably gonna clean this up. And then the cross validation again is more just for tighter understanding of what your true score is, so that you know, oh, I added, you know, I tweaked the number of neurons in my second to last layer, right? It's like, you really want to know, did that go up by 0.1 or did it go down by 0.1? And if you're plus minus 0.5 on any given run, then you can't know whether that helped or not.
And it becomes more important based on data set size too.
Yeah, how big was the validation set?
It was 35. What's actually, I had it in here somewhere. It's 35% of the total data, and the total data was like 25,000. So it's like 8,000, I think.
Okay, and then some of those classes, this is a really imbalanced data set, right? A couple of those diseases are really rare.
Yeah, I didn't do a plot of it, but yeah, that's true. So that can make a difference, and maybe the stratified sampling would help with that.
Yeah, they're at like 12,000 of one example and 1,000 on another. They're really biased, what I noticed. And I have a question actually. Have you tried, Neil, to fight duplicates in this data set? And I have a question for everybody. Does duplicate somehow influence the inference, like our classification after all?
I didn't try to address duplication. I guess I assumed that the data set was, since it was a Kaggle competition, that it was, maybe that's a bad assumption, but I didn't expect there to be duplication.
Yeah, I played with this competition a bit. There are 800 duplicates across the different classes.
Wow.
Yes, and I have a hint for you, actually. There is a competition from 2019, the same competition. So everybody just combining the data set, there are 5,000 more examples. So this is what I did. And then I tried to find duplicates, and I found 800 duplicates. And moreover, I collect, honestly, I distributed to all classes through different folders, and then I tried to find the cross duplicates, and I found like 150 duplicates within the different classes, like similar images in different classes.
Sergey, how are you finding duplicates, by name or by image?
I have a piece of code here. I just copied it from some other people notebook, and I don't remember. I used hash. I compared hashes. There is a technique. So
so they are exactly duplicates, you're saying? Exactly, like.
Yes. No, I put the similarity like 90%. There are hashes for every images, and I compared hashes. I just converted hashes into matrices, and I just compare each image to each image, compared the numbers. So yeah, I have a piece of code somewhere, but.
So if there truly are duplicates, I would strongly I would strongly
I opened up the 8 pictures, and they were literally the same.
So when you modify when you alter the data, whether it's adding more data or removing duplicates or whatever, do you just create your own data set in Kaggle then? Do you just download the whole data set?
I download
it. I'm just wondering, like, mechanically, how do you do that? Like, because right now I'm just running it straight out of the Kaggle,
Yeah, if you open up your notebooks, there is a 2019 data set available publicly, so you can connect it. Yes, I ran. What I did actually first, I tried to run and remove duplicates automatically, but it took me like 1 hour. Then I just gave up. I delete the duplicates, and then I just move everything to CSV, like with no duplicates. And yes, I had a list of files, so they are like unique. And then I just used that CSV. I just uploaded that CSV with no duplicates, and then I just use that duplicates to, I mean, that CSV to train my model.
Huh?
So did you notice removing duplicates, did it improve or hurt your performance again?
Can you repeat?
Removing the duplicates, did it help with your performance or no?
It actually worsened the performance, like
Oh, really?
4.5%. I don't know how it works, honestly, because that's why I asked you, does it somehow influence the training, the duplicates, if we have them or not?
That's weird.
Yeah, when I combined two data sets from 2019 and 2020, I received the best performance.
I understand that because you have additional data, so I understand that.
Yeah, yes, but then I removed duplicates, the performance became worse.
A lot worse or just a little?
A little, like 0.5%,
could just
but
be
they
some
were even.
randomness.
I would think it's just a fluke, because essentially by having two copies of 100, examples, all you're doing is upweighting, you're double weighting those examples.
Yes.
So
But
so
then
long as
you just-
examples are decent examples, right? If you had like a mislabeled training example and you increase its weight, that's probably a bad idea. But otherwise, when you're talking about thousands of them, if a couple of them are double weighted, I don't think it really, in the grand scheme, by luck, it could help you or hurt you, but I don't think in the grand scheme it's really doing anything.
When you say it hurt your performance, was that in the test set when you submitted, or was that in your validation set?
In a test set. Oh, no, validation set, I'm sorry.
Okay, so I think that's where, so if the duplicates showed up in your training, one in your training set and one showed up in your validation set, you're gonna do really well on that example, right? So it couldn't, so if you remove the duplicates, now you won't have that scenario and your performance will go down on your validation set.
Oh, yeah.
Neil, do you mind stop sharing your screen so we can look at each other better? Thank you.
Yes, absolutely.
Thank you.
That's a great point, David. Yeah, so accidental leakage just through duplicate
Could happen.
images.
Say it again, David, I missed it.
So if he has duplicates and he splits his test in training, and one image from that duplicate set is in training and one's in validation, he's going to be able to predict that very accurately, right? Then when you drop your duplicates and you no longer have that situation, your performance might go down some because it's, as Ted said, you have leakage happening.
Yeah. Good to know. Any other tricks you tried, Sergey, except for removing duplicates?
Different augmentations. Yeah, there is a kernel, good kernel with Augmentations, and I picked up some of them. I didn't try TTA in the end so far. We're still working on the model. We received like 87%, which is out of 1,000 competitors. So we're really down in the leaderboards. So we're trying our best to get. And I was excited when I saw you're gonna try this competition today. So I was really surprised and excited.
Nice. How long have you been working on this? How long have you been working on this competition?
Couple of weeks.
Okay.
Yeah, it was really challenging to remove all duplicates. Tried different ways of doing it. Yes, and the best model so far I found the ResNet 5032. This is the same family of models which Neil used. Other models behave, worse. So.
And you're loading a pre-trained ResNet 50 and you're just training the dense layers? Or
yeah, I loaded pre-trained model. And I use PyTorch. You said dense layers?
So are you training that ResNet 50 or are you freezing that part?
No, I didn't train ResNet 50.
Okay.
Interesting.
So let me open it up. Projects. Yeah, and I had the questions about submissions. I didn't really submit it. No, so I was really interested in the part of submission. So as far as I see, there is only like CSV file should be generated in the end of the competition and then just submitted, right? And there is no really automatic way to submit it right away. You need to save your model, then have a second notebook. Or you have to upload it manually, right?
you have to create a separate notebook that doesn't use a TPU and doesn't have the internet connection. And that second model, therefore, is not doing training either. So it's got to read the model from a file that's already saved from the other. And then the only thing that the notebook has to do is read all of the test data from the path that they specify, and then perform inference on it, and then generate a CSV file with the results and save it, and that's it. And then so I think when you submit it, what Kaggle does is they run your notebook in their kind of hidden space where when it runs it substitutes the test data that they have with what you had in your notebook, and then they fetch the CSV result and they compare it against the ground truth, and they get your score that way.
One thing to keep in mind if you do TTA, the test train augmentation, is I think your final submitted notebook has to run within 9 hours. Is that right, Neil? Do you recall?
Yes.
That's right. Yeah, they give you that sounds about right, a 9-hour limit. I mean, it shouldn't take anywhere near that long if all you're doing is inference. I guess maybe for the traditional Kaggle, you may have your notebook might actually do the full-blown training and then do actually inference on the test data. But here, like I said, you can't do that here because you can't do it without a TPU. So when I submitted it, and it ran really fast. I mean, it just took a few minutes to get the result. So if you have any questions about the submission piece of it, feel free to reach out to me, because I actually did get it to work.
Cool.
All right. Well, I'll just close my. I just want to thank you for the opportunity for. I'll just close my. Oh, I was going to say thank you for the opportunity to do this. I definitely learned a lot, and this competition goes on for like another month, I think. So I'm definitely gonna, since I've gone this far with it, which isn't really that far, but I'm gonna try some of these things. You guys gave me some good ideas, so thank you.
Great job, Neil.
Awesome, great job, yeah. And Sergey, if you want to share your notebook with us, or if you want to present maybe your notebook in one of our next sessions, let us know. Happy to host you. Sorry, Vladimir.
Yeah, sure. Yeah, sure. Should I somehow add you?
Kind of comment or question to Neil. Okay.
Sorry, Vladimir. I have a hard time hearing you.
Do you hear me? No.
Sergey, let me share our Slack with you. You can join us on Slack.
Okay. I have some communication problem.
Let me share our Slack with you. Join us on Slack. Vladimir, I think your mic is.
Okay, so do you hear me? Do you hear me now?
Barely. Yes. Mic is
gone.
Barely. Yes.
Okay. So you mentioned something about let's say some pre-processing that goes in another domain, wavelets or something like this, and then feeding into the deep learning network. Actually, we're doing something very similar. Now, this in general makes some sense, and if you know what kind of transform to do, what kind of features to get, because what we're doing by going to another domain makes some features. I think this can help in this case, especially the fact that you're looking at some specific texture, not kind of object or something like this that you're trying to recognize. So I wonder if you try it and see, I mean, try different wavelets, or just do some experiments. It may take a lot of time to find the right pre-processing, but I think the performance may increase. And now our experience just feeding raw data, it's not always the best thing to do. Especially if the network is kind of generic type, not really designed for this kind of learning inference. Just an idea maybe.
Yeah, we briefly mentioned that in the beginning, that maybe some more traditional image processing techniques might work well. My challenge with that is, how do you incorporate that information? Somehow you need to extract that feature and incorporate it with the features you're getting from your coordinates, right? So your model will be kind of like a hybrid. We'll need to read the information from the image as well as from your statistical processing package, combine them into one vector, and then do the classification. That looks like a hybrid model to me, or like
I was thinking about just trying to feed them into the dense layer, combine it with the.
Sorry about it, I mean, if you don't mind, I'll keep muting you until you're ready to talk. Go ahead, Neil. If you don't mind, I'll keep muting you.
Sorry.
Yeah, there's
So,
definitely an echo.
Instead of feeding the raw image, instead of feeding the raw image to the first layer, you feed the, let's say, the transformed image. So you go, for example, you go from image to some wavelet. There you have again 2D, and then you feed this to the first layer. So you don't use the whole network, not just inject it somewhere. But instead of feeding the raw data of the image pixels, you feed the transform representation. And in this case, I think wavelet is indeed better choice than Fourier transform. Much better.
Got it. So you're saying you basically have a lambda layer as the first layer, like a pre-processing layer, and that's where you do the wavelet transformation. That's where you feed the rest of them. That's where you do the wavelet.
Yes. Yeah. So like in convolution layers, the first layer basically you do some filtering, and this kernels usually is like whatever you train eventually becomes like type of edge detection, depending what you're trying to do. But this is just I'd say a very, very basic way to condition to go from a raw data from, let's say, signal domain into first feature map.
Yeah.
You can do something better that is dependent on the actual characteristic of the signals, like in the traditional machine learning, you have some features. But now you have a deep network that does much more work than a traditional, let's say, support vector machine. Things like this. So just to exploit the fact that you already know something about the signal that you're trying to classify. And just put it into some general purpose deep learning network that. Okay, that's good.
So one approach would be to actually transform it, like you said. I was thinking more of using two data sources, the raw pixels you're reading, as well as the wavelet information, then combining them in your model. But you're saying just use the transformed version and use that as an input to your model. Yeah, I'm curious how they perform.
Yeah, that's what I, yeah. I'm curious. That's so the thing is that in order first, I mean, if you, let's say you take with wavelets, but you have to select carefully your wavelet. So you have to understand what actually you're looking at in order to pick the wavelet that will give you the right time frequency representation that will help your neural network. And this is, let's say, the human part of the engineering, because you really kind of have expertise of the signal. You know the signal, and you know what you're looking at. And after you have it, you pick up the right transform, you feed it into the network.
Got it. Cool. Awesome. Thank you, Neil. Thank you, friends, for joining us. Thank you for sticking us all the way to the end. This was a long, interesting session, and I love the conversation in the chat as well. I can share that in our Slack channel. And Sergey, whoever is taking the competitions, if you have anything you want to share with us, please join us on Slack. It's always interesting when we learn from each other and support each other. So I highly encourage you to do so. Cool. Let me share my screen with some closing remarks here, and we can wrap up. So next couple of sessions, we're going to switch gears a little bit. We're going to move from computer vision to reinforcement learning and look at a little bit of game AI, as well as try to build our own navigational or intelligent bots to navigate in space in a game AI. That'd be an interesting session. After that, Robert's going to present a session for us on a project he worked on in the past related to the bike share data. And another that hasn't been posted yet, that event, we'll be posting it soon. Another one is the last event that will conclude this Kaggle Mini Courses challenge. These are the last two sessions of this. We'll have some of the some of the Kaggle content creators. I invited them to have a session with us. We're going to ask them a little bit about the process of creating these courses, what they find interesting, challenging, some of the cool projects they're working on in their own personal lives, and getting to know each other a little bit better in the greater Kaggle community. So that should be fun. That's it. I want to thank everyone. Thanks for joining us. Hope to see you next time. And I wish everyone a good night. And I'll stop the recording here. I'll leave the floor open if anyone has any comments or feedback.